Hey everyone, here to introduce chapter 8. This is one that we temporarily skipped and we kind of are doubling back to, and we're just going to kind of get a little taste of what chapter 8 is all about in our last couple weeks of school. So in chapter 8, it's our second round with geometry. In chapter 4, we did the area of rectangles, triangles, and trapezoids, and of course squares as well. And we know that we had different formulas to find those different areas of the shapes. So in chapter 8, we're going to be looking at area again, but rather than simply a two-dimensional flat figure, we're actually going to be looking at 3D figures, ones that have depth to them, okay? So we're kind of doing a little bit of combination of lessons 1 and 2 today. So let's first talk about some of the vocabulary that you're going to be required to identify. And some of this, if not most of it, has been touched upon in elementary school. We're just kind of revisiting it again. My son is doing 3D shapes right now in first grade, and some of these words are popping up in his first grade class. So one thing we want to talk about is our faces and our vertices. Okay, you saw these on your notes. I have a few manipulatives here of different shapes we're going to look at, okay? So the faces of any three-dimensional shape are the flat sides, okay? So something like a sphere, like a globe or a basketball, they don't have faces because it's not flat, it's all rounded. So we're going to be looking at shapes that have faces, okay? So the individual flat sides are what we call faces, okay? The next vocab word that you were introduced to in the notes were vertex, or the plural is vertices, and those are corners, okay? So different shapes have a different number of vertices, and that would be true of all of that type of shape. And then the last would be edges. We're not going to do a whole lot of work with edges, but edges are where two faces, I can't hold it, where two faces meet. So like the ridge of this box, okay? So the two shapes we're going to be concerned with in our first day today are cubes and rectangular prisms. So cubes, unfortunately, I have to pretend that this is a perfect cube, even though it's not. A cube would be a square in 3D. So the properties of a square are that all four sides are the same. So in a cube, it's as though we took a square and stretched it out to make a 3D figure. So I've actually taken, you guys have Magna-Tiles at home or a younger sibling with Magna-Tiles, okay? These are squares, true squares, not like my phony tissue box. And I've made a cube out of it, okay? Meaning it is just as wide as it is tall as it is deep, okay? That would be a cube. In a cube, there are 6 different faces. If we were thinking about 1, 2, 3, and 4, top and bottom make 5 and 6. So there's 6 faces. That is true about any cube, whether it's handheld or massive. Okay, 6 faces. Another shape that we're going to be looking at is a rectangular prism. Okay, so I've got some store brand Wheat Thins and some Ritz crackers. Okay, both of these boxes are rectangular prisms. They are rectangles that have been given depth to be 3D, okay? So remember, properties of a rectangle are that you don't have the same width and length, or height in this case, okay? So we can tell that this box is definitely taller than it is wide. And then we also have the depth, okay, how thick it is, okay? Still has 6 faces though, the front, the back, side, top, and bottom, okay? The Ritz box is the same thing, a rectangular prism. The width and the height are not the same, neither is the depth, okay? Still 6 faces though. So what we're gonna be looking at today is naming our shape. If it's a cube, all 4 sides are the same. It is the same width, height, and depth. Okay. If it's not, it's a rectangular prism, meaning it's a little bit taller, a little bit wider. It's not all equal, okay? The other thing that I want to show you is that on these shapes, and the same would be true for a rectangular prism. The properties of a square and a rectangle, which are the 2D versions of these shapes, are that opposite sides are the same. Okay, so if I simply wanted to talk about just the front of this box, we know the properties of a rectangle are that this side, whatever the length is, 7 inches, is the same as this side. Okay, the top is the same as the bottom. Okay, so when we look at the surface area of a shape, we are looking at the area of all of the faces added together. Okay, so we would have to use the appropriate formulas to find out the area of the front face, and the area of the top face, and the area of the side, and the area of the other side, and the area of the bottom, and the area of the back. And then add up all those numbers. Now, if some of you are like, what? I gotta find area 6 times and then add it together. Well, the good news is properties of these shapes can save you some work. So let's use my Magna-Tiles, for example. It's a little bit easier. So I already told you that this is a cube because they are the same width, height, and depth, okay? But the same would be true. I just don't have rectangular pieces, Magna-Tiles, so I couldn't build one. But the same would be true. So here with a cube, I color-coded this, okay? My front here is this purple color, okay? I put on the back the same purple color, okay? The top is this red color. I put on the bottom a red color, okay? And then the sides, I used yellow, okay? So if my Wheat Thins box were Magna-Tiles, it would be the same thing. If I know the area of the front, I also know the area of the back. They're the same. If I know the area of the side, I know the other side. They're the same. If I know the area of the top, I know the area of the bottom. They're the same. Okay? So yes, you have to find 3 different areas, but that's better than 6, right? 50% off. Okay? Either way, big takeaway is that surface area is area of all of the faces, all the sides, added together. Okay? One last thing I want to show you before we go. I wish I had a better way to show you this. I might even try scooting this around. I should have test drove this before I showed you guys. Okay, and that is a net. In your notes, I believe you saw a version of a net. It's as though we were to not break the shape apart, but flatten the shape. Okay, so when this box of Ritz crackers is all eaten by the Jari family, this box, I'm sure as your family does too, is going to go in the recycling bin. And usually we flatten it, okay? So like we open up the flaps and flatten it out, okay? That's what a net is, okay? It takes the 3D figure, which for some of us is hard to see because a lot of times you're looking at a 3D figure that's flat on a piece of paper, like a textbook. And it opens it up, it flattens it, okay? So I'm going to see if I can kind of like